Okay, so I know this is the last talk in what's been like a long program of pretty intense talks. So I want to start off with something actually very naive. So there's this old subject of congruences of modular forms. And here's an example. So let's take that first cusp form of level 1. So this is sometimes called the delta function, and it has this explicit power series, a Q series, which looks like this. And so this is in weight 12 and level 1. Now let's look at this guy mod 11. So mod 11, we're going to see an interesting congruence. So I'm going to start rewriting this, but now I'm going to pull out a 1 minus q to the n squared. That leaves a 1 minus q to the n 22, and 22 is divisible by 11. So mod 11, I can kind of rewrite this as following way. And it turns out that this thing is again a modular form of weight 2 and level gamma naught 11. Okay, so I think naively speaking, there's something kind of surprising here because there aren't very many modular forms. And then clearly the probability that two modular forms agree in the nth Fourier coefficient is less than 1. So reasoning in this way, you would predict that the probability that you have such a congruence is 0. And so this is something which should basically never happen. However, it actually happens quite often. And so that's indicative that there's some more structure going on. So actually this thing has a simple rep theory explanation. And so we know that we can think of modular forms kind of in general of weight k, let's say just level 1, so gamma 1, z. We know that kind of the Hecke eigenforms which appear here, their Hecke eigensystems are incarnated in some kind of cohomology. Sim k minus 2 of the standard representation. And so similarly, modulo p, your Hecke eigensystems will be incarnated in the cohomology of this thing mod p. So sim k minus 2 of fp squared. But when you think of this representation mod p, this action of this group will factor through SL2 fp. And then you're going to start to see that these representations, as k varies, collapse a lot. And so there's not so many representations of SL2FP. There's a lot of collapsing of these representations, and therefore there must be a lot of collapsing of the Hecke eigensystems that you see. And I claim, in fact, that if you kind of understand the representation theory of this group, then it's a priori obvious that there will be some congruence between these two spaces. So let me actually come to this board to just give some reminders about representation theory. So what does the representation theory of a reductive group look like? And I'm going to take G to be simply connected here. Okay, so one thing I've learned from this conference is that the kind of younger generation of mathematicians doesn't really think about representations so much. So for them, you can think of these as vector bundles on the stack BG. But I'm a kind of older generation, so I'm gonna continue to think about representations. Okay, so let's start kind of at the beginning. So we know that the behavior of this thing depends on the ground field. So for, let's say, complex numbers, the irreducible representations of G over the complex numbers are in bijection with dominant weights. And so here are some examples. So for SL2, you have the weights, and then you take the dominant ones, so you take the integral points in this half. For SL3, here's the weight lattice, and we would take the dominant weights in this cone. And the the representation of highest weight lambda, I'm going to call W of lambda for the Weil module. Okay, so for example, for SL2, the highest weight is an integer n, and this thing is can be thought of as the polynomials in two variables x and y of degree n, homogeneous degree n. Okay, so that's how this kind of classical representation theory works. Now we're ultimately interested in modular representation theory. So for us, this coefficients will be something like FP or FP bar. And what happens in that case? It's very different. So representations of G in this case will be, well, they'll be in bijection with dominant highest weights. So actually, there's a risk if you just look at this formally to think that somehow it looks the same. So in order to kind of de-emphasize that, I'm going to call this irreducible representation L of lambda. And I want to emphasize that you shouldn't think of L of lambda as being like W of lambda. W lambda is something which you could create integrally and reduce it mod p. So you could make this mod p, and it would not be the same as this. That thing would in general be reducible, and this thing would be kind of its Sokal. So for example, here, the Weil module of weight p is still this thing, polynomials of two variables of degree, homogeneous degree p, but now in characteristic p, it'll contain as a stable submodule the polynomials in x to the p and y to the p. It's the miracle of characteristic p that this thing is actually stable under SL2. And so this is what we would call L of p. And notice it's the Frobenius twist of L of 1, the representation you get by taking the kind of standard representation and Frobenius twisting it. Okay, so just to kind of draw a picture of the situation, we know how to describe the irreducible representations here in terms of their characters. And the picture is quite simple. So you can just draw this kind of triangle where the nth symmetric power is on the nth row, and the characters are given by the rows in this triangle. Yes, thank you. So if we wanted to draw an analogous picture of the irreducible representations here, then we would maybe start out with this triangle. And then we'd start drawing in the same characters at the very beginning. But then once we reach the pth Weil module, then things would be different. So we would actually see a very kind of small dimensional representation. We'd have to cut out a triangle from this picture of characters. And then we'd continue in this way. And then once we reach the edge again, we'd cut out another triangle. And so in contrast to this picture, the characters of these irreducible representations have this kind of fractal structure. And that is a reflection of Steinberg's theorem, which says that all the L of lambdas can be built from ones where lambda is in a very small box by the operations of tensor product and Frobenius twist. So maybe I'll try to illustrate this. So basically, the representation theory is dictated by, qualitatively dictated by the hyperplanes where the weights paired to 0 with roots or simple roots. But in characteristic P, it's dictated by when this is 0 mod P. So it would be natural to then continue drawing these affine hyperplanes. And the box which I'm referring to is kind of a region cut out by such hyperplanes. So something like this, or for SL2, and for SL3, it looks like this. So all the representations, all these irreducible representations outside of this box can actually be described in terms of ones from the box just by these two operations. Now, why do I mention this? After all, we're interested really in representations of G of FP, not these algebraic representations. So it turns out that the irreducible representations in characteristic P of G of FP are in bijection with the box. So it's a fact that the irreducible representations all extend to irreducible representations of the algebraic group, which must therefore be irreducible. And if you think about it, the ones which are Frobenius twisted, that the Frobenius twist does nothing to this group. So the Frobenius twisting and tensoring will create a kind of redundancy, telling you that nothing outside the box could possibly be irreducible when you restrict it to here. So only the ones in the box will matter because exactly of this Frobenius twisting property. And so the representation relevant here is L of lambda restricted to G of FP. And in Brandon's notation, this is what he called F of lambda. So those are all of these irreducible representations. Now, earlier in this week, other kinds of interesting representations of this group which have come up. For example, one could take just parabolic induction. This is a construction of a kind of different flavor. This is something which we are interested in, and they did come up in the previous talk as well. So I'm going to single this out. I'll call this R identity chi, in anticipation of a more general construction where you can take, as Charlotte was doing earlier in the week. Oh yeah, I'm also assuming G is split. Yeah, thanks. Yeah. Yeah, that's true. That's true. Absolutely. Nevertheless, G is split for this discussion, let's say. Okay, so this is a Deligne-Lustig representation as introduced by Charlotte, where W is an element of the Weil group, which kind of tells you in her language which torus to take, or would maybe in another language tell you which Bruhat cell to take, and then chi would be a character. And a priori, this would be a representation characteristic 0, but we could consider its reduction mod P, at least as an element of the growth indeed. So that's what I'm going to call maybe specialization of this characteristic 0 representation to characteristic P. Yeah, maybe we should emphasize. So one can investigate the Breuil-Mezard conjecture for more general groups, but let's keep this discussion to split groups for now, for simplicity. I think eventually we'll discuss results for split groups over unramified extensions. If you were to replace this FB by an FQ, you would basically just enlarge this box so that it has side length Q instead of P. Okay, so so where was I going with this? So I promised you that it should be kind of clear a priori that a congruence must exist in between those two spaces of modular forms. So let me rewrite those. So let me think of modular forms of weight 12 and level 1. Their Hecke eigensystems are incarnated in the cohomology of SL2Z with coefficients in, well, weight 12, as we discussed, that is what we're now calling this irreducible representation F10. And modular forms of weight 2 and level gamma naught 11. So that's cohomology of gamma naught 11 with coefficients in the trivial representation. But we could rewrite this using Shapiro as cohomology of SL2Z with coefficients in this guy. So our identity, let's call it 0 for the trivial character. Okay, and now the point is that there's already some relation between these two coefficients here. So more generally, when you write down this kind of parabolic induction, so I guess I was calling it SL2. If we want to compare this, let's say I, this is I regarded as a character. If we compare this with this highest weight representation Fi, well, by definition, the highest weight representation has a vector stable under the Borel. And this is, by definition, is induced from the Borel, so there must be this kind of map. And a dual consideration would produce a map kind of the other way. And counting dimensions, you would see that this must be accounting for everything. So this decomposes in the growth in V group as the sum of these two things exactly. So this representation here, in fact, contains this one as a summand. And so it is clear a priori that any eigensystem which occurs here must occur here as well. Okay, so now we've explained this kind of zero probability event, but not all congruences are explained by this kind of consideration. For example, there's this phenomenon of companion forms that's not explained by this. So let me give you an example. Well, I'm gonna partially give you the example. So the example, which is due to Elke's, I mean, it's found by computer search, will occur at the prime 107, and there will be two modular forms involved. So one of them will be called F. And now, to remember what this is, okay, so F is going to be a modular form of weight 26 of level 1. Delta is as before, and E4 and E6 are the usual normalized Einstein series with those names. So then there will be a G, and G will be in weight 82. And G will have a very long expression, which we're only going to write the first few terms of. So G will be E4, E6, delta, E4 to the 15, subtract, I give up. Okay, so what we see here is that this, in that representation theoretic language, would be coming from the irreducible representation F24. And this form comes from this Eichler-Shimura relation from a representation which we're calling F80. So there is some kind of congruence between these two. It has to be twisted a little bit, so I don't notice I haven't written down exactly what it is, but it's coming from two different irreducible representations. So there's no way it could be explained by that same kind of simple consideration. This thing is only possible because 25 plus 81 is 106, which happens to be one less than this prime. We'll raise this board. Let's see. I want to. So actually, I'll stay on here. So actually, Brandon already explained what is the mechanism for this kind of congruence to occur. So let me just kind of review what he said in the context of a slightly more generality than we're talking about here. So G will be a reductive group over a number field, and we're going to be talking about a conjectural picture. So it's growing out of work of, well, Serre. So I'm actually not too familiar with this history. So someone give me a list of names to copy down, which I'm trying to do. So Serre, Ash, Stevens, Breuil-Mezard. And then the formulation I give was really due to Emerton G. And so what does this conjectural picture say? So first of all, we're going to have a notion of mod P modular forms for G. And the way we're going to think about it is that a mod P Heck eigensystem. Let's say for simplicity that it should be an eigensystem occurring in the cohomology of G of Z with coefficients in some FP bar representation of G of FP. Okay, so this is the kind of thing, let's label this M, the kind of thing which we regard as the general group analog of these coefficients of Hecke eigenforms. And part of the conjectural picture is that we're going to have an associated Galois representation. Okay, so let's say it would look something like this. Think valued in the dual group. And of course, this global Galois representation knows the eigensystem, right? So these eigensystems, they're the eigensystem of the pth Hecke operator is somehow encoded in traces or kind of characteristic polynomials of Frobenius here. So the global Galois representation knows about the eigensystem. But the question of which weights could give rise to a given eigensystem is conjecturally determined only by the local Galois representation. And so that kind of, but it could be determined in a kind of subtle way. So that motivates the consideration of the Emerton G stack. As Brandon introduced, the stack of representations of a local Galois group. And what's supposed to happen is that still conjecturally, there exists some map from irreducible FP bar representations to cycles on the underlying reduce of this thing, which in particular is in characteristic P. So let's call it the top Chow group of XEG over FP. And this is the thing which he called sigma. Sigma in here goes to the Breuil-Mezard cycle Z sigma, which is in here. And it's supposed to be kind of the locus of representations which can arise from eigensystems in this particular weight. And so in particular, the eigensystem M should occur in weight sigma if and only if the associated local Galois representation lies on this Breuil-Mezard cycle. So that is the significance of the Breuil-Mezard cycle. Okay, so this is the kind of general conjectural picture, and how is it playing out in this particular example? So what happens in this particular example is that there's a Breuil-Mezard cycle for weight 24, where the generic representation, at least on inertia, is supposed to be an extension of omega, the cyclotomic character to the 25th one, and then something trivial. Then some extension, which is generically non-zero. And then the Breuil-Mezard cycle for this weight, 80, looks like an extension where this exponent is 81, omega to the 81, 1, and then usually some non-trivial extension. And so these two look different, right? But they intersect at one point, which is where this extension class is 0. Actually, they intersect if we kind of regard things valued in PGL2. But because of this coincidence that 25 plus 81 is 106, it exactly in this case, when these extension classes are 0, you get a point. This has a potential to be a global kind of central twist of this thing. And so what is happening in this example is that these two forms, they happen to have their local representations land exactly at this point. And for that reason, they can admit a congruence. So indeed, it is a low probability event, which is why one has to search pretty hard to find the example, but it occurs, and it occurs because of this kind of picture here. Okay, so this is meant to motivate that if we want to understand the phenomenon of congruences, we should understand the geometry of this Emerton G stack and understand what these Breuil-Mezard cycles look like. Okay, so this is also something Brendan kind of explained, but I'm just going to rehash. it briefly. So the way we're looking at this thing, well, so it's a moduli space of local Galois representations. And so in particular, we're interested in like mod P Galois representations. We're also interested in like characteristic 0 Galois representations. And what one finds mod P is that this thing, it's a formal algebraic stack, but one can take its underlying reduced, then it's that's an actual algebraic stack mod P. And this thing is a union of things that Brandon called X sigma, where sigma is exactly a Serre weight or an irreducible representation of G of FP. So this is Serre weight. So it's of the form, so call this F of lambda, where lambda was in that box. So that's what this thing is. Maybe it looks like, some finite union of things. They all have the same dimension. And now here, among the characteristic 0 representations, we distinguished certain classes. So there was a locus called X. Sorry, so it's very convenient that this talk went right after Brandon's, which seems to have been kind of a coincidence because the schedule was decided before the abstracts. So that's very convenient for me. But I will also have to try and keep my notation consistent with his, which means I have to kind of shuffle my Greek letters around. So I think he called this X lambda tau. And what is this? So mu, sorry, X mu tau. So mu is going to be a dominant weight, which, or dominant co-character, dominant character, which records the Hodge-Tate weights of your Galois representation. And tau is an inertial type. Which records the kind of inertial action. So this is a potentially crystalline, let's say, locus with Hodge-Tate weights, mu plus this half sum of positive roots and inertial type tau. And there are many of these things. So in this sort of, among these characteristic 0 Galois representations, of course, ones with different Hodge-Tate weights are kind of all different. So I'm going to just draw them like this. So there's an infinitude of all these loci. And these guys, when you specialize them to characteristic P, they have the same dimension as these. So it will be the case that if I specialize P to 0 of this, the cycle of this thing, it will be some kind of linear combination of these irreducible components here. So let's call them n, mu, tau, sigma, x sigma. And of course, this is a finite sum. So here you have something like p to the n thingies, p to the n minus 1, I guess, in my notation. And here we have, of course, infinitely many of these x mu taus. There's already infinitely many mu's. And for the taus, we'll be interested in, it'll be also something like p to the n of them. But these infinitely many things, when you specialize in the characteristic 0, they kind of collapse in linear combinations of these finitely many basis elements. And so this is on the Galois side, but that's supposed to be reflective of the way that there's infinitely many modular forms in characteristic 0, like partitioned by all the possible weights and level structures. But as we saw, when you take those things mod P, there's a lot of collapsing among them. And the basic point of the Breuil-Mezard conjecture, which I will formulate, is that the kind of nature of the collapsing of these loci in characteristic P should be consistent with the nature of the collapsing of the kind of representation theory from characteristic 0 to characteristic P. Exactly because the automorphic representation theory and the Galois representation theory are supposed to be kind of behaving the same way. Okay, are there any questions? So I'm going to now reformulate this Breuil-Mezard conjecture. Okay, I'm going to say it slightly differently to how Brandon said it. So I want to write it like this. I'm going to say that the conjecture is there exists a map from the growth in D group of representations of G of FP in characteristic P to this kind of top child group of the emergent G stack, which I may as well take as underlying reduce, doesn't affect this thing, and then it's in characteristic P such that when I take a representation of this thing, which kind of comes from characteristic 0 in the way that you would expect to see for modular forms of a given weight and level. So I'll take a vial module, which records the characteristic 0 weight, tensored with this inertial representation tau. So that's a representation of G of ZP and characteristic 0, which is kind of combinatorially extracted by the inertial local Langlands correspondence from the Galois inertial type tau, which was on that board. So, okay, what's the point? This is like a representation characteristic 0, but I can kind of specialize it to characteristic P, and then it will land inside this growth in D group. And I'm going to ask that this thing under my map here is sent to the specialization of this potentially crystalline locus from characteristic 0 to characteristic P. So the characteristic 0 Galois representations, which this guy sees, are exactly meant to be the Galois representations which can arise from automorphic forms of this weight and level. And then we're saying as we take things to characteristic P, it should somehow be consistent with this picture. And this map here is supposed to be the map which sends the Serre weight or irreducible representation to the Breuil-Mezard cycle. Okay, so this is just a reformulation of the way that Brandon posed it. So his formulation of the Borel-Mazard conjecture was like, there exists cycles such that when you decompose this guy in characteristic P, you see the same multiplicities as when you decompose this thing into characteristic P with respect to this basis. Okay, so this is a free abelian group generated by these sigmas. So to give this map is the same thing as to specify these cycles. And to ask for this property that I've written here is the same as asking for the property that he did. So that just wanted to explain kind of what is the translation between the two formulations. Now, I think the first 4 or 5 times I saw this conjecture stated, I didn't really know what I was looking at because there's a lot of superscripts and so on. So let me just try and like give a kind of down to earth psychological interpretation of this. Okay, so we are observing some phenomenon, congruence of modular forms. So we think of that as like gravity. It's like the theory of gravity, and we want to like understand, how can I understand, you know, how quickly things fall, and if two things of different weight fall, they land at the same time, and things like this. So we postulate that the theory of gravity is governed by a finite number of fundamental constants, and that's what these Z sigmas are. So maybe we think gravitational force only depends on like mass and distance and doesn't depend on space and time. So okay, we'll make this guess. We have certain fundamental constants which then pin down exactly how the thing works, and then there's like an infinite number of possible experiments which could contradict or affirm or be consistent with the way our theory works. And so that's what this second part is. So it's like we have certain fundamental constants which basically amount to the n mu tau sigmas, which are on that board. And after these constants are decided, then there's infinite number of possible tests which will verify whether or not the thing is consistent with experiment. So I mentioned this because in practice, and as Brendan already alluded to, we're going to try and make progress on this conjecture in the form of like, well, okay, we're not going to be able to verify every experiment for every mu and every tau, but we'll be pretty satisfied if we can verify a lot of them. And in particular, for any proposed map to be reasonable, we better verify more experiments than kind of the input variables. So this thing here is a free abelian group of rank about p to the r, p to the n. Okay, so this is free of rank p, approximately p to the n, because that's approximately how many irreducible representations there are, a very rough approximation. And now here, the number of mu's is of course infinite, and the number of taus is also something like np to the n. So, or at least the one, yeah, okay. So if we can verify, a number of these equations, which is much larger than this, then that will be actually pretty strong evidence of the truth of this conjecture. So with that said, I wanted to sort of talk about what's known. So as Brandon discussed, kind of the case of GL2 over QP is basically completely known thanks to work of Kisin, Pascunas. Sorry, this is not joined. Okay. Kisin, Pascunas, and others. And it uses a tool which is really not available in other situations, namely the local Langlands correspondence for GL2 QP. So it is really fundamentally limited to this situation. The case of GL2 over finite extensions of QP, where one specifically takes mu to be maybe, I think it's like trivial in my normalization. But from a Galois perspective, it's this Barsati-Tate case, Hodge-Tate weights 1 and 0. So this case where you perform only those experiments is known to due to Kisin, G Kisin, kind of at the level of deformation rings, and at this stack theoretic level, which I formulated actually was done by Cariani, Emerton-G, and Savitt. And this is again using certain specific features of GL2. So first of all, one can kind of do automorphic arguments for GL2 over totally real fields in much like better generality than one can handle arbitrary groups. And also, as Brandon mentioned, there's something simpler about the Breuil-Mezard cycles, or at least what they're supposed to be for GL2 because of some representation theoretic fact that it's for GL2 and GL2 only that all the irreducible characteristic P representations lift to Weil modules. So for GL2 and GL2 only, the conjecture is exactly specifying as part of the statement what this is supposed to be. And there's in fact a quote which I've copied down from the Emerton-G book about the higher dimensional case. So they say, we expect the situation for GLD when D is bigger than 2 to be considerably more complicated than that for GL2. Experience to date suggests that the weight part of Serre's conjecture in high dimensions is consistently more complicated than anticipated. So it seems unwise to engage in speculation. This is something which they say. So let's see. So that kind of highlights how impressive it is that the authors from the previous talk were all here, in fact. Daniel Ley, Bao Le Hung, Brendan Levin, and Stefano Mora were able to prove kind of strong results towards Breuil-Mezard in kind of arbitrary dimensions. So next I'm going to talk about the case of GL(n), where n is arbitrary, but tau is very generic. Sorry, this will be over K, which has to be unramified over QP. And the type tau is very generic. So as I mentioned, or maybe tau is usually something, at least when tau is generic, it's going to be a delinealistic representation. RW chi, and W is in the Weil group, and where is chi? So chi is in something called the fundamental alcove. So this is too tall. So if one tiles the weight space by all the affine hyperplanes where lambda paired with alpha check is 0 mod p for any root alpha check, then one gets some kind of tiling, and it divides it into alcoves, and chi is in this alcove. And chi being very generic means that it's very far away from the walls of this alcove. So it's concentrated somewhere like that. So what do they actually prove? So they show that if you fix a finite set of these possible Hodge-Tate weights, then let's see, what do they prove? Then there exists some assignment of Breuil-Mazard cycles such that that equation, that experiment with this Hodge-Tate weight and type holds if chi is far enough away from the walls. So let's just say it's very far from the walls of this alcove, where very far depends on n, and it depends on the set of mu's. But it does not depend on p, and that's somehow crucial. Because other than the fact that it depends on these and it's large, one doesn't know how large in any sense. It could be like a gazillion to the bajillion to the factorial of the size of these sets. We have no idea. So for any given p, there may be nothing which is sufficiently large. But as p increases, eventually there will be stuff in here. So that's what they prove. Is that accurate? Okay. So the new theorem that we're working on with Bao gives a more effective result. So it shows that, first of all, there exist these Breuil-Mazard cycles such that the equation will hold whenever sigma, which is f of lambda, is at least 2n plus kind of the size of chi from, size of mu from the walls. So it's telling you that there is a region here where we know that all the kind of experiments where your type chi is in here will hold, for example. So just to give some sense, so the size of this alcove, the side length is about p. And p is going to be therefore pretty large. That's the psychology we have in mind. In particular, it's larger than n, and n is some kind of basic unit where if p is less than n, then there's no regular things anyway. So n is kind of the basic step size, and p is large. Okay, so this gives it somewhat more effective control over when you're going to have this equation hold, or when this experiment will work. And just the back of the envelope, remember we said that the assignment of these things is free a priori, so there's about p to the n equations. roughly up to, and then the number of equations which we're testing here for us is about the square of this thing, so about p to the 2n. Sorry, this is just 3 variables. About p to the n free variables, about p to the 2n equations, and for them, they get big O of p to the n equations. So they can increase the size of this set to get kind of an arbitrary constant number of times p to the n, but that comes at the cost that this thing will increase uncontrollably as well. And it may be like a trillion to the billion to the million to the 10,000, who knows? Okay, so that's one thing. And then you may look at this and say, well, you know what, I don't really care if you can produce these cycles that partially satisfy equations, even if it's a lot of equations, because really I'm after a conjecture where everything is satisfied. I don't want some partial cycles. I want the correct cycles. So towards that, we can say that if the Breuil-Mezard conjecture holds, if it's actually true that these cycles exist, so there will then be some kind of true Breuil-Mezard cycles, right? The true ones which work for all the equations, then necessarily this will agree with the ones we have as soon as this sigma is at least 3n from the walls. Okay, so in this picture, the chi is drawn from this alcove, but actually the sigma is drawn from the box that was before. So the box in this SL3 case will look like this. And what we're saying is that you have to go slightly smaller than the blue thing where you knew all of the equations worked. And that's the same in all of these translates. But if you go slightly inwards, then you're going to be guaranteed that you have the right cycles as long as the conjecture is actually true. They would also get a kind of uniqueness statement. So when enough of their equations hold, their cycles will be uniquely determined and they will be equal to the true things if the true things exist, and they will be equal to our cycles. And the basic reason is just that as soon as you have more equations than variables, as long as the equations are independent enough, that forces the thing to be unique. So are there any questions about this statement? Yeah? Well, no, so tau is like RW chi. And so like I see it. This is not the relevant quantity here. Yeah, thanks. Whenever chi is bigger than this from the walls, then that thing works. For them, okay, so yeah, let's draw the picture of, so for the theorem on the right, the set of all possible experiments, at least, the set of all possible chi's which feature into experiments, or the possible taus which feature into experiments, is this fundamental alcove. And the ones for which we can guarantee that something works is like this blue thing. Now, what does their thing look like? Well, it looks like the following. So there's a question mark, because in a given prime, one doesn't know how big this needs to be to work. One knows as the prime increases, there will be something eventually. Yeah, sure. Yeah. Let's see time. Okay. Any other questions? Okay, so there are some differences in the approach of these two theorems. So for the theorem on the left, as we just heard about, the approach is kind of a vast generalization of this patching method. And what they do is they make local models, and the purpose of the local models is to show that certain Galois deformation rings are irreducible, and then one can patch, and then one can follow the method of G and Kissen. And so as a kind of byproduct, a kind of pro of their thing is that it gives some global automorphy results. And then depending on how you formulate things, it gives results towards Serre's conjecture, the weight part of Serre's conjecture. And so in summary, one gets like global results as a byproduct of this, the proof of this theorem. So these are kind of very nice additional features. We don't get any of those. In fact, our whole thing is local. But that could be regarded as a pro because then, in fact, everything we do, 99% of it applies for kind of general G, which is simply connected. But there's a major part missing, which is that the Emerton G stack hasn't been constructed with enough knowledge to actually formulate the conjecture as I stated it. So at the very end, when one tries to connect our construction to the Emerton G stack, then the Emerton G stack is kind of missing. But because what we do is kind of applicable to general G, simply connected, then I think there's like a lot of optimism that when the thing is formulated, then the proof will also be there. Okay, so I'd also like to mention that actually when we started doing this thing, we were not pursuing kind of the ability to carry out more experiments, the ability to satisfy more of these equations. Actually, what we wanted to do was understand the Breuil-Mezard cycles, which came out of, which we kind of knew it existed, at least if P is large, thanks to their theorem. So as Brandon mentioned, the proof doesn't really elucidate what is the actual nature of this cycle. And in fact, Serre already raised the question in his original article. Like he kind of guessed in our language what this should be for SL2 based on global considerations, but he asked, like, is there kind of mod P local Langland's philosophy, which would give some a priori conceptual prediction for what this should be, and which you could then generalize to other groups. So that is kind of actually the thing which we really are pursuing. And to illustrate the kind of answer that comes out, I will say a little bit about what it is that we're doing. So just shift the time. Okay. So it begins with a certain fantasy. Oh, and I should say, actually, there were some inspirations for this fantasy. So there's the work of Breuil, Hung, and Stren, which in the locally analytic case constructs some kind of analogous locally analytic Breuil-Mezard cycles as microlocal supports. And it was independently mentioned to me, probably other people, by Matt Emerton, that like these potentially crystalline loci also look like microlocal supports in some sense. So here's the fantasy. So we have QP, and we know that this thing, it's a kind of, well, by now old wisdom that this is analogous to a surface, a topological surface. And this would lead you to expect that the Emerton G stack is analogous to a symplectic manifold. So let's call it S. So here's a picture of a symplectic space, cotangent bundle of a circle. And the reason is not complicated. It's because the tangent spaces are supposed to be these H1s. And this analogy is on the basis that QP has a two-dimensional Poincare duality, so the H1 would then carry a symplectic form. Then these potentially crystalline loci, their tangent spaces are these things which are usually notated H1F. And the thing about this subscript F is that it's constructed in a kind of Lagrangian way. It is its own self-annihilator. So this will lead you to expect that, or sort of imagine, that these loci were meant to be thought of as Lagrangians inside a symplectic space. So let's say L. So our cartoon of the situation is we have this symplectic space, then we have various Lagrangians swimming around inside of it. And there is another area of math where one finds these kinds of pictures and one is looking at this kind of structure, the structure of, this kind of space of Lagrange inside a symplectic manifold. So that's called homological mirror symmetry. And what one finds here is that one tries to take these Lagrangians and assemble them into some category, Fukaya category, and the objects are roughly these, and the morphisms I won't even try to say anything about. But the point of the theory is that one predicts that this category has another description or is equivalent to some kind of category of derived category of coherent sheaves on some kind of mirror space. So the basic thing I just want to take away from this is that one expects in this kind of situation to have that the structure of the Lagrangians inside the symplectic space, the kind of patterns among them, are governed by some kind of totally different structure of a totally different nature here. And this is in some sense the same situation we're after here. We have these loci, these Galois loci, and we expect that they're governed by some sort of representation theoretic pattern. So that's the fantasy. Well, then one also has to not just fantasize, but like face reality. Why? Oh, yeah. I mean, so the question is, do I also have a fantasy of what Y should be if S is the Emerson G stack? And yeah, I'm going to just proceed, and maybe your question will be answered by that. So, but the first thing I want to remark is that in reality, this fantasy is a lie. And we know this local Tate duality, it's actually twisted. So the Emerson G stack, it's not actually symplectic, and then these potentially crystalline loci, they're not actually Lagrangian, and so the whole thing kind of falls on its face. So that's at first disappointing. But remember, we're not trying to make some kind of fancy Fukaya category of the Emerson G stack. We're just after some coarse numerical phenomenon. We're just after kind of the structure of its top dimensional components, irreducible components, and like how they arrange themselves and what patterns they have. So for our purpose, it's enough to kind of approximate this fantasy by something which is actually true. So the fantasy can be approximated. Oh, what do I mean by that? So as I just said, we're interested in like the structure of the irreducible components of this thing. So we're interested, let's say, in the top child group of this. Let's just say mu tau. And because we're only interested in this kind of coarse combinatorial data, we're free to kind of replace this space by a different space. Why not the spaces from the previous talk? So these guys, LLLM, worked hard to construct algebraic varieties which smoothly model this thing. So why don't we take the thing which I want to say was called mu nabla tau from Brandon's talk. But a remark is, actually, we don't really care that it's like a smooth local model. We don't care that this thing is unibranch. All we care about is that it has a similar kind of like very coarse appearance of top dimensional components. So this thing, I don't know, maybe the Emerson G stack looks like this. Maybe this thing looks slightly different. Maybe sometimes it's not unibranch. We don't care. Because we're actually after this very coarse information where we can again approximate this space by something else, which we're going to call Y gamma. And what is this Y gamma? Well, it's called an affine Springer fiber. And the important thing about it for our purpose is that the particular one, so gamma is somehow cooked up from tau by a formula which I'm not explaining, but these particular affine Springer fibers really are Lagrangian inside some natural symplectic space, some space of Higgs bundles for the dual group. And this thing, in fact, admits completely integrable system, a Hitchin fibration for which this is a Higgs fiber. So it is arising naturally as a Lagrangian subspace. And because of that, it's possible to hope, and it is in the end true, that this enjoys some kind of isomorphism to a thing of a different nature, namely the top K group, the K group, zeroth K group of coherent sheaves on the flag variety for G, and then I need to take T equivariant coherent sheaves. So this relationship, I think you can think of it as some kind of shadow of this homological mirror symmetry. And this is something that was we saw in work of Brezhnev, Kovnikov, Boishida, Alvarez, McBreen, and Yoon. In fact, they pursue the full categorical statement, of which we only need the statement at the level of K0. But you see here that there's some transition between the group and the dual group. And that exactly is provided by this HMS. Okay, so we've kind of, in terms of this approximation, we've kind of gotten to one side, right? We took this Emerton G stack and we approximated it by the geometry of some actual Lagrangian. So we just need to do the other half now. So we were interested in K0 rep FP bar G of FP. And turns out, and this is a kind of thing which was recognized a long time ago in modular representation theory, that the structure of these representations is similar to the structure of representations of the Lie algebra of G. So that's something more algebraic a priori. So how does this work? Well, remember I said this guy, its representations actually, the simple representations extend to the algebraic group. They're called F lambdas. And when you have representations of the algebraic group, you can differentiate them and get representations of the Lie algebra. However, you didn't see many representations of the algebraic group this way because the other simples of the algebraic group come by Frobenius twist and tensor product. But the Lie algebra won't see those either, because when you do Frobenius twist and you differentiate it, you get 0. So in that sense, this kind of redundancy created by this Frobenius is witnessed in the same way for these two groups. And that sort of explains why these things look similar. And the reason why we wanted to get here is because then we can try to localize representations of the Lie algebra onto the flag variety. So that is, again, a kind of old idea. It's Beilinson-Bernstein localization, except if you're familiar with that from characteristic 0, you would have expected to see not coherent sheaves on the flag variety, but D modules on the flag variety. So but it works out because I sort of lied to you here, because I need to ask that these representations of the Lie algebra actually extend to the group. There's a condition in characteristic P. There's a kind of P center, which I need to ask to be 0. And that reflects in the statement that these D modules should have P curvature 0. So when I do this Beilinson-Bernstein localization, then I'm going to land in a special class of D modules, P curvature 0. And in fact, by principle called Cartier descent, that's the same as coherent sheaves on morally on kind of the Frobenius twist of the flag variety, because things were split and so on. It doesn't actually matter. Okay, so then to kind of make this really correct, I have to do some other bells and whistles, which I don't really want to explain. So this is just a kind of brief impressionistic account of what we want to do. But it's here, the point is we've now forged the path from where we are at one end to where we end up. So we have these representations, we can localize them, we can descend them, we can apply this mirror symmetry and get actual physical cycles on this space, which we call the singular support of L of lambda, because it really is, if one unwinds what's going on here, it really arises as the micro support of some constructible sheaf somewhere. And then one can undo this approximation and eventually get back to the Breuil-Mezard cycle for F lambda. So basically, the proposed construction of these cycles is following this rather convoluted path, and that's how one arrives at our candidate for these Breuil-Mezard cycles. Okay, so clearly this is, yeah, I should end, right? Yeah, so so let me just conclude with the thought that, like, in some sense, this complicated process doesn't exactly elucidate what it is. What it does elucidate that this thing, this kind of like fundamental constant that we encounter in the Breuil-Mezard conjecture, is also some numerical pattern which one encounters like in symplectic geometry and geometric representation theory. So at least we're not kind of alone in the mathematical universe. And let me end on that note. Yeah, thank you.